All right, so what we're going to do today is we're going to look at some more application problems for exponentials, but we're going to start by looking at an equation that we've already dealt with, this compound interest equation, and specifically we're going to look at the part that involves how many compounds we have. So in theory, we know that the more compounds, the more interest you should get. So what we're going to do here is take a look at a graph of y equals this function. If we were to take and graph it, it would do something like this. And if we were to look out as n goes to infinity, or compounding as many times as we possibly can, we find that this problem actually kind of levels out. And it levels out to a number of roughly 2.718-ish. And that's a special number. They call that number E. All right, and the guy who actually looked at this formula first was a man named Euler, E-U-L-E-R. And so they gave him his own constant E, which is equal to 2.718. And that's the number you see on your calculator. Now with that, we look at two new equations that talk about growth and decay. One being the standard growth and decay equation. And in this case, you'll notice this K value right here. A lot of the times they'll give this to you, but sometimes they don't, which makes the problem harder to solve. A continually compounded interest problem, you will know to use this formula because they say it's compounded continually and not quarterly or semi-annually or yearly or daily or whatever. So anyways, let's take a look at our first example. This is a continuously compounded problem. We start with $7,000. We compound continuously at 4.34%, so that's 0.0434, and we do it for 10 years, so that's P e to the RT. And we want to find out how much money we have in the end. And that's just a calculator problem. So we pop that, and we end up getting roughly 10,803.93 dollars. Taking a look at the next problem. Now it says at the end of an investment, we have $892.69. And we're looking for the amount we invested after continuously compounding, so we use that P e to the RT again, at 5.5%, so that's 0.055, and we do this for 3 years and 2 months, so that's 3 1/6 years, right around there. Again, it's a calculator problem. We're going to take and find out what this quantity to the right equals, and then divide it into the other quantity. And after doing that, we get roughly $750. Moving forward, this problem's a little bit more difficult because we know we have an amount to start with at 330. We know it quadruples every 30 minutes, and we want to know how many there's going to be at 515. And the equation we're going to use, since this is not a compound interest problem, is n equals n sub o e to the kt. Now they didn't give us a constant, so we're going to have to find that. And that's going to pose a problem. First of all, we start with 1024, but we don't know what we finish with. So in theory, we have two unknowns, but we really don't, because we know it quadruples every 30 minutes. So if I quadruple 1024, I get 496. And that's some e raised to an unknown k but I have the time. That's 30 minutes, so 0.5 of an hour. Now the problem with this is we don't know how to solve for an unknown variable in the exponent. So what we're going to have to do is use our calculator to try to solve this. So let's fire that up. And what I'm going to do is take and graph the two functions. First, 1024 e to the 0.5 x, or k times 0.5. And I'm going to graph another equation of 4096. And when I take a look at the graph, I notice that the two intersect. Where these two intersect is going to be the value of k. Now I set my window to go from -10 to 10 for x's and -10 to 5050 because I know they have to intersect at 4096 somewhere. And that's why I'm able to get the picture here. So to find this intersection, I go second, calculate, and I go to intersect, number 5. And it's going to ask me for my first curve, and we'll make that the exponential. I press enter. Second curve will be the horizontal. Hit enter again. It gives me that guess, and I hit enter a third time. And this will give me the value of k, which is the x value. So k equals 2.77. Now that I know k, I can go back and solve this equation again for the time lapse between 3:30 and 5:15. So let's go ahead and do that. I start out once again with 1024. I have some e raised to the k, which I now know is 2.77. And I'm doing this for a total of 1 hour and 45 minutes. So 1.75 hours. And that'll get me my final amount. So now this is turned into a calculator problem. And I end up with an answer of about 130,479. Last example. We know that a isotope has a half-life. That's a decaying life of about 28 minutes. We want to know how long it would take a sample to decay to 37% of its original mass. All right, again, kind of a difficult problem. We don't know how much we start with, but we know it goes to 37% of the original mass. So if I start with, let's say, 100 grams of something, and we can start with anything. I'm just using 100 because it's easy to take 37% of that. Then that goes to 37. And that's e to the k. Again, I don't have the k value. T. Now, all we know is that the half-life of this isotope is 28 minutes. We don't have a k or a t for going from 100% of something to 37%. So once again, we're going to have to take and set up a different equation. Start at 100%. We have e to the k. Now, I know how long it takes to go to 50% of the original. Half-life, that's 50%. And it takes about 28 minutes. So we're going to make our t, in this case, minutes. So again, I have my unknown in my variable, and I'm going to use my calculator and graph it to solve. So here we are again with our calculator, and we notice that we have our 100 e to the 28x equaling 50. I graph it, and I notice once again I get this intersection. My window this time I set from x going from -1 to 1 because I couldn't see really what was going on unless I zoomed in on it. Then I went up to 75. And now I'm going to take and calculate once again my intersection. And I'm going to hit enter 3 times. 1, 2, 3. I get an answer of negative 0.0247. So I get K equals negative 0.0247. Once I have this value, I will plug that into the K in this equation over here, and thus get 37 equals 100 times negative 0.0247 times t. And once again, I'm going to have to use the calculator and graph this to find my t value. So once again, here's our calculator. We've got the function on the right, 100e to the negative 0.0247x, and then I've put 50 on the right. Actually, we want to put 37 because that's what it's going to intersect. So let's put 37 there. And then we're going to take and graph this. Now, I've done a little pre-checking, and my x goes from negative 10 to 100, and my y goes from negative 10 to 75 because I know I'm going to have to see at least 37. So I graph that. Setting your window is going to be the hardest part, and we get this picture. So I'm going to find that intersection. So I calculate that, intersect, and hit the enter button 3 times. 1, 2, 3. This gets me a t value. T is equal to, that was roughly 40.25. And those are minutes. And this kind of makes sense because we know that if we start with 100, then half of it's going to go away in 28 minutes. So that gets us to 50. And if I went another 28 minutes, that would be 56 minutes, I would get to 25. But I'm going to 37, so it's not quite another 28 minutes. I get a total of 40 minutes going by. The calculator stuff's going to be a little bit tricky. Work on it. I'll do one tomorrow most likely. Here are some questions for you to answer. Thanks.